Hello friends, and welcome to this lecture on Programmable Logic Controller, short form for which is PLC. It is part of our unit number 4, which is the last topic in our curriculum. As we have been discussing for the past few lectures we discussed about microprocessors, we discussed about microcontrollers. In fact, Programmable Logic Controllers have been in use for the past maybe 30 years or so, particularly in cases of numerically controlled machine tools or CNC machines, computer numerically controlled machines, and some automation applications. PLCs have always been in use for dedicated applications. We'll just try to understand few basics related to programmable logic controller. The programmable logic controller or a programmable controller is a digital computer used for automation of electromechanical processes in modern factory automation. For example, control of machinery on factory assembly lines, as well as heating, ventilating, and air conditioning, that is HVAC, plastic injection molding machines, and commercial washing machines, etc. These PLCs have been in use. PLCs are members of computer family using integrated circuits instead of electromechanical devices to implement control functions. They are capable of storing instructions such as sequencing, timing, counting, arithmetic, data manipulation, and communication to control industrial machines and processes. This figure illustrates a conceptual diagram of a PLC application. Now, this diagram tells you about the process of the machine which is to be controlled. Your programmable controller gives out the field outputs to control the given machine, and there will be a sensor which will measure the system parameters or the process parameters, and it is given as an input to your programmable controller. And this is how programmable controllers are in use in industry. Why PLC is a big question. Now, hardwired panels or relay logic are very time consuming. See, till that time, before the usage of PLC, all the automation was done through hardwired panels, and many relays were actuated by using these hardwired devices. It was very time consuming, and there was no flexibility as such. That used to be a rigid type of automation. If a dedicated application for maybe a bottle sealing plant was designed and developed, that automation was useful only for bottle making plant only. If I need to make use of the same automation circuitry for some other application, it was not possible there. And it was very time consuming to make those changes as well. So hardwired panels, so relay logic, are very time consuming to implement due to wiring and debugging related issues. In need of another controller which is faster and operates in real time, withstands vibrations, temperatures, humidity, noise, has inbuilt interfacing for inputs and outputs, is flexible and adaptable, easy to program, reprogram, easy to troubleshoot and maintain. That controller should be able to consume less space, requires less wiring, and comparatively cheaper. So this was the need then, and then these PLCs came into the picture. What is the selection criteria for programmable logic controllers? First and foremost is what is the requirement of a given application. If I have a sorting machine, maybe vegetable sorting machine, what are the specific requirements, measurement requirements, what are the control requirements, what are the actuating requirements, how the sorting should be done. So if that picture is very clear, I need to define what is the control logic that I want and what type of programmable logic controller I should go in for. What are the input output requirements? What are the memory requirements? What are the CPU requirements? What is the software requirement and operator interface that is required? See, if the operator is trained, he'll be able to understand what are the commands that are coming up on the screen. If an operator is semi-skilled or unskilled operator, that interface has to be symbolic sort of thing. Instead of alphanumeric, it should be symbolic interface. So what kind of interface is required? what sort of communication is required, what sort of environmental conditions to which this PLC will be subjected to. So based on these points, these criteria, a proper PLC is selected. What are the components of a PLC? This is the plant. The plant parameters are sensed and given to the input module. The input module gives it to your CPU. The CPU contains your processor and memory. The power supply is provided and it generates an output, and that output is the actuating outputs which actuates the plant components, so to say. So, and this cycle continues. These are the basic components of the PLC. But what are the input and output devices those are used? Input devices provide inputs to the control system. In case of discrete state process control, now we have already discussed this discrete state process control. Now, what is the difference between discrete state and continuous process control? If we just take an example of a steel factory or any process industry for that matter, the raw steel that is molten and then it is rolled, re-rolled and reshaped, and maybe the eye sections are developed, the structural members are developed. So it's a continuous process, and the control requirement for such process is also of continuous process control requirement. But in some cases, as we talked about a milk packaging industry, so those things are happening discretely once in a while, or maybe in any furnace control, whenever the jobs are there, those are to be heat treated or those are to be heated. So that will be happening discretely once in a while. So in case of discrete state process control, the inputs are of two state specifications, such as I require limit switches, which is either open or closed. I need comparators, which will be higher, giving me either high signal or low signal, or push buttons. Those are either depressed or not depressed. So these are the discrete state process control requirements, where the states of control are of only two nature, either on off, open closed, either high or low, either pushed or unpushed, or depressed or not depressed. And output devices accept outputs from the control system. In discrete state process control, the outputs accept only two state commands, such as lights are on and off, motors rotating and not rotating, solenoids are engaged or not engaged. Now, some input devices, let us see, the push button, PB stands for push button 1, which is normally open, right? And this is normally closed push button, right? Momentary action push button. The limit switches, we already know these limit switches. LS stands for limit switches, normally open and normally closed. Pressure switches, PS1 stands for pressure switches, which define the limiting pressures, normally open and normally closed. The temperature switches, so based on temperature, those are actuated. So these switches are temperature limit switches, normally open and normally closed. So level limit switches, LLS, normally open and normally closed. And what are the output devices? Either motor, either solenoid or light. So these are the output devices. Now in the PLCs, the working circuit diagram, let us say, that is called as a ladder diagram, because it appears like a ladder having steps. It is called as a ladder diagram. Then now the left hand pole or left hand column is called as the input side of the ladder diagram, and this right side pole is called as the output side of the ladder diagram. And these lines, those are called as rungs of a PLC. So input side, output side, and these are the horizontal are the rungs of the ladder diagram. And the signal flow is from left to right, come down to left to right, left to right, left to right, and then left to right. This is how the circuit is executed, or the actuation is executed. And various components are the input devices and output devices are accordingly placed in this ladder diagram. So this is the first one, the push button, okay, which is normally open, and this is normally closed. And then the output devices, maybe lamps or maybe whatever are your output devices, maybe motor, maybe solenoid, So those will be the output devices, those will be mentioned here. Sample ladder diagram. Constructing and logic gate. Now and ending we know. This and this should be on so that the light will be put on, isn't it? The simple ladder diagram for and logic gate. Okay, so push button 1, push button 2. These are this and this are pressed, then only the light will be on. And logic gate is normally closed. Now this truth table we already know. This is off, this is off, the light will be off. One is on, other is off, light will be off. First one is off, second one is on, still off. Only if both are on, the lights will be on. This is a AND logic gate. Similarly, other logic gates can also be constructed by using the ladder diagram. Now, relay sequencers. Now, PLCs are normally used in sequential logic control. If I take the case of a press machine, hydraulic press machine, so what are the requirements? The punch should come down, and before the punch comes down, what are the prerequisites? The sheet should be placed just above the die, and then it should be properly locked, isn't it? Properly pressed, properly locked, that is the correct word. And then only my punch should move down, and after punching it should be lifted up and the indexing should take place, the sheet should be moved forward, the punch part should fall down. So there is a typical sequence of operations which is involved in this pressing machine tool. So based on that sequence of operation, we use various components in our PLC automation. Before the PLC control sequencing and safety, interlock logic for manufacturing was mainly composed of relays, cam timers, and dedicated closed loop controllers. One way to provide a discrete state controller is to use physical relays to put together a circuit that satisfies the requirements of the ladder diagram. When a program has been wired into relays that make up the relay logic panel, it has been programmed to meet the ladder diagram. If the event sequence is to be changed, it is necessary to rewire all or part of the panel. It may even be necessary to add more relays to the system. We're talking about these older relay sequencers. The move from relay logic controllers to computer-based controllers was an obvious one. The input and output variables of discrete state control systems are binary in nature, just as with a computer. Many of the control relays of the ladder diagram can be replaced by software, which means less hardware control. It is easy to make changes in a programmed sequence of events when it is only a change in software. There are no hardware or hardwired changes required. Special functions such as time delay actions, counters are easy to produce in software. Now, what is the architecture of a PLC? You have a processor, you have programming software, the input module and the output module. Simple architecture of programmable logic controller. Programmable controller can be studied by considering the basic elements as shown in the figure. The processor, the input and output modules, and the software associated with it. Let us move further. The components in PLC. Now the central processing unit, which is the heart of my PLC, in which I also have memory to store program data as well as the data, variable data. Then power supply is required. Then the input module, input sensing devices will be there, and they'll be sending signals to my input module. And then optical isolation will be there between the CPU and input. Optical isolation will be there between the CPU and output. Yes, and these can be, CPU can be interfaced with my computer, even desktop computer, so that I can have display over there. And then the output module will actuate either a solenoid or a motor or a lamp, whatever are my output load devices. Okay, so these are the basic components: input module, output module, CPU, memory, power supply, programming devices, and communication channel. The input module, you have number of channels. Different PLCs will have different number of input channels. I can have 4 input and 4 output channels in a particular brand of Siemens PLC. Allen Bradley also manufacture your PLCs. So different manufacturers provide different variety of my PLCs. Now in this case, I have got 3 channels for supply, and then I have input limit switches, limit switch 1, push button 1, limit switch 2, and power supply is given. And this goes to the processor. Figure shows the typical wiring to a PLC input module. The input module examines the state of the physical switches and the other output input devices and puts their state into a form suitable for the processor. It is able to accommodate a number of inputs called channels. If the switch is closed, the input will be 24 volt DC, and if open, it will be 0 volt DC. 24 volt DC or 0 volt DC. The input module converts this into the 1 or 0 state needed by the processor. The input module convert real-world voltage and currents to signals the PLC can understand. Since there are different types of input devices, there is a wide variety of input modules available, including both digital and analog modules. So you have discrete or digital module, use 0 or 1 to depict the state, or I can have analog module, use numbers to depict the state, that is 30 degree, maybe temperatures, okay, or pressures. The switches normally work from 0 to 24 volt DC. Pressure switches work from 4 to 20 milliamperes, and temperature input devices work between 0 to 10 volt DC. In the output module, so this is my output module. From this processor, the control signal has come. Now the actuation has to take place. So either I have a lamp or a solenoid or a motor, right? So that the actuation will take place. Okay, figure shows the typical wiring to the PLC output module. The output module supplies AC power to the external devices such as motors, lights, solenoids. Internally, the output module accepts a 0 or 1 from the processor and uses it to turn on or off a device. An output module can have one or several channels per unit. Each channel is usually provided with an indicator light to show whether the particular channel is being driven on or off. So physical description, either I can have a valve which is operated for between 0 to 10 volt DC, fan which is operated from 0 to 120 volt AC, or a light bulb which is operated from 0 to 24 volt DC. Then the processor is a computer that executes a program to perform the operation specified in a ladder diagram. It performs arithmetic and logic operations on input modules, on input variable data, and determines the proper state of the output variables. Then CPU and memory. CPU is the brain of the PLC, is the central processing unit. It executes various logical and sequencing functions by operating on the PLC inputs, mainly the sensor information to determine the appropriate output signals for the actuator. The processor is a microprocessor, very similar in its construction to those used in personal computers and other data processing equipment. Memory, it is tied to the CPU, and it is the PLC memory, which contains the program logic, then sequencing information, and other input-output operations. The memory for a programmable logic controller is specified in the same way as that for a computer, may range from 1K to 48K of storage capacity. Memory types are ROM, RAM, and erasable and reprogrammable ROM. The power supply, power supply of 115 volts is used to provide power to the PLC and any other modules. Power supplies come in various forms. Power supply modules that fit into one of the slots in a chassis of a PLC box. External power supplies that mount to the outside of the chassis. Standalone power supplies that connect to the PLC or input-output through a power cable. Embedded power supplies that come as part of a PLC block. Or switching mode power supply that we use in a computer. Similar sort of thing is there for PLC power supply as well. The programmable device. The programmable device, the PLC is programmed by means of a programming device. The programmable device, the programming device is usually detachable from the PLC cabinet so that it can be shared between different controllers. Different PLC manufacturers provide different devices. A simple teach pendant type, like our remote, a teach pendant type device similar to those used in, that is called as a teach pendant in robots. If you have seen in big process industries, you have the cranes operated by a remote or a cabled control device that is called as it is similar to a pendant. PLC programming keyboards are also used, and CRT displays. Nowadays, touchscreen displays are also available for programming. And the communication channel CPU uses the data bus for sending data between the constituent elements. It uses the address bus to send the addresses of locations for accessing stored data. It uses the control bus for signals relating to internal control actions, and it uses a system bus for communication between input-output ports and input-output units. The buses are the paths used for communication within the PLC. The information is transmitted in binary form, that is as a group of bits, with a bit being a binary digit, either 0 or 1, that is on or off states. The term word is used for the group of bits constituting some information. Thus, the 8-bit word might be the binary number 0010, 0110. These are few examples. Each of the bits is communicated simultaneously along its own parallel wire. So types of PLCs. Single box type PLC is commonly used for small programmable controllers. Typically, such a PLC might have 6, 8, 12, or 24 ports, 24 inputs, and 4, 8, 16 outputs, and a memory which can store some 300 to 1000 instructions. This single box type of PLC. A modular PLC or a rack type PLC consists of separate modules for power supply, processor, input module, output module, and memory. So brick type PLC, a rack type PLC. Various racks you can find for memory, processor, right, input output devices. In PLC operation, the operation of the PLC can be considered in two modes. It is in the input output scan mode and the execution mode. Now the input output scan mode. During the input output scan mode, the processor updates all the outputs and inputs, the output state of all inputs, one channel at a time. The time required for this depends on the speed of the processor. It scans and resets the inputs and outputs. Then the execution mode. During this mode, the processor evaluates each rung of the ladder, each step of the ladder, each rung of the ladder diagram sequentially, starting from the first rung and proceeding to the last rung. As the rung is evaluated, the last known state of each switch and relay contact in the rung is considered. And if any true path to the output device is detected, then that output is indicated to the energized, that is set to on. At the end of the ladder diagram, the input-output mode is entered again, and all the output devices are provided with on-off state determined from execution of the ladder diagram. All inputs are sampled, and the execution mode starts again. Now, how the PLC addressing is done? Input channels addresses are from 00 to 07, output channels 08 to 15, internal relay 16 to 31, timers and counters 32 to 39. To identify the input-output devices, the PLC uses the device address or channel. Its address designation depends on the type of programmable controller. Our table shows the typical address designation for different input-output devices. Now, program diagram interpretation. In a program diagram, the on-off state of the output of the rung is determined by testing the elements of the rung for a true or false condition. If a complete true element path to the output exists in the rung, then the output will be made true or on. Interpretation continues. The symbol for a no contact indicates that the device should be interpreted as false if the contact is tested and found to be open, and true if it is found to be closed. It is to be examined on, and if on, it is true. The symbol for normally closed, upper one was normally open, normally closed contact indicates that if it is tested and found to be closed, then it is false. And if tested and found open, it is on. It is to be examined off, or if off, it is true. Use a normally closed push button switch to turn on a red light. The normally closed push button to turn on red light. Okay. Using NC switch to turn on a light. with relay logic and with PLC programming. Okay, the button turns the light off. With relay logic, the button turns the light on, and with PLC program, the button turns the light on. Right? This is a PLC program, your relay logic, and then this is also relay logic. This is a control relay. Programming of PLCs, ladder logic used for machine control, functional block diagram. So there are various ways, either ladder logic is used for machine control, or FBD or functional block diagram is used for process control. Called ladder diagrams because they resemble a ladder with two vertical rails, supply power, and as many rungs, horizontal lines, as there are control circuits to present. So this column, input side, this column, output side. This is the rung, first rung. Likewise, I can have number of rungs, input side and output side. Ladder diagram, how the scanning is done, the power flow from left to right, left rail to right rail, the signal, control signal moves from left to the scanning, takes place from left to right, once again left to right, left to right, left to right, and this is end rung. Okay, input and output. Then corresponding this input, I'll be getting some output, normally open, so it is output will be on, normally closed, input is this and output will be off. Elements of a ladder diagram, control relay, normally open switch, normally open control relay, normally closed. Then I have got normally open limit switch, normally closed limit switch, and then output side, I got motor, solenoid or light. This we already seen. Limit switch type, push button type, limit switch type, pressure limit type, temperature limit, and level limit type. And logic, A and B should be closed to get the light on. The symbol of AND gate. OR gate, A or B, so that the light will be on. A or B. Either one is on, the light will be on. Either one is on, light will be on. And both are on, still light will be on. Not logic, just inversion, 0 to 1, 1 to 0. This we already seen. So we have different examples. The PLC timer function, the program timer function plays an important role in PLC applications to provide for needed delays in some manufacturing sequences. Okay, and to specify the period of time that some operation is to last. While actuated by a true path, the timer begins to accumulate time in the form of ticks. Each tick is worth a certain amount of time. Like ticking of a clock, the timer is preloaded with a certain number of these ticks. When the accumulated time ticks equals the preload value, the timer itself becomes true. The timer only counts while it has true input. If the input becomes false, then true again, the timer will reset to 0 and start to count again. PLC timer function, okay. This is how the diagram is drawn, the ladder diagram is drawn. Yes, we already seen this. I think that these are a few examples of the counter function. Okay, timer function we have seen, then the counter function. A counter is a PLC counter is a programmed function that counts every time the input changes from false to true. If in one scan the input is false and the next scan the input is true, the counter increments. No further count will occur until the input goes false again and then true. The counter has an address and a preset number of counts. When the preset number of counts have been accumulated, the counter becomes true and can activate some other part of the ladder diagram. I think if we take some examples of PLC programming, that will be very easy to understand. These are a few examples for counter function. We just go through it, and I'll post some of the notes related to simple applications of PLC programming logic, so that you can easily develop a ladder diagram for such an application and write a program for that.